Welcome to CSEC Physics with me, Marvin Lee. Today we will begin a series of episodes in which we work past papers with and for you. We'll be starting with the January 2020 paper 2, and I hope that during these episodes you grab a pen, a book, a calculator, and you follow along. Now please note, we're not asking, or we're not doing this rather for you to cram the answers. We're working the papers so that you can understand how the answers are achieved, obtained, or how you get there. So please, don't cram the answers, understand the answers. Welcome to this past paper episode of CSEC Physics with me, Marvin Lee. Welcome back. I said earlier I will be working the 2020 paper 2. Now, in an odd twist, I'll be working from question 6 forward instead of question 1 backward. So I'll be working through the paper from the back to the front. Now, some bits of information. The paper is usually 6 questions long and around 2.5 hours in terms of time allocated, and it's worth about 100 marks. If I do remember correctly, and I think I do. Question 1 is 25 marks, and the other 5 questions are 15 marks apiece. Now, I'll read from my printout of question 6, and hopefully you can follow along. So, question 6A, it says, 3 emissions, alpha, beta, and gamma, from a radioactive source are subjected to a uniform magnetic field perpendicular to their path, as shown in figure 5. Draw the 3 rays to represent the path of each of the 3 emissions, alpha, beta, and gamma, on figure 5 as they pass through the magnetic field. So, let me quickly sketch the diagram. Now, these X's are drawn to indicate the magnetic field is traveling into the board or the page or the paper. Okay, they're traveling into the board away from the viewer or away from you. And the the radioactive source is put at the bottom here. And they want you to indicate by drawing lines what the paths of alpha, beta, and gamma will be. So just like we're working paper from the back to the front, we'll deal with the radiations from the back to the front as well. The last radiation listed was gamma. Now, gamma rays are unaffected, totally unaffected by electric and magnetic fields. They have no mass and they have no charge, and as a result of which they're not affected by the magnetic field. Now, the beta particle, which is negatively charged, will trace a path that looks something like this, and the alpha particle, which is positively charged, will trace a path that looks like this. Gamma, straight through, unaffected, alpha, with its positive charge, going to the left, and beta, with its negative charge, headed to the right. Now, the difference in the shape of the path between alpha and beta is due to the masses of the emissions involved. The gamma ray is the only ray. Alpha and beta are particles. They have mass. Alpha particle has significantly more mass than the beta particle, and as a result of which it will take much longer to turn. The beta particle being much smaller and lighter will turn more sharply. It's kind of like the difference between a compact car taking a corner or a large 18-wheeler truck. The truck, because of its size and mass, will take a lot longer to turn. The compact car will turn very quickly. And this is how the 3 emissions are affected by a magnetic field. For further explanation, just to clarify, there is this rule called Fleming's left-hand rule. Left hand is the motor rule. Now, As charge moves through a magnetic field, it will be deflected based on this. This is the direction of motion or deflection. This is the direction of the magnetic field, and this, the middle finger, is the direction of current. So, using Fleming's left-hand or motor rule, force or motion, field, current. Now, the direction of current is taken as conventional, so that means we assume current leaves the positive and travels to the negative terminal of the source. I'll explain that further shortly. The magnetic field is going into the board. This is the direction of positive charge, or in which positive charge would move. And there we have magnetic field into board, positive charge going up, and our thumb. I know it's really hard to do. Let me put the paper down. Okay, force, field, current. If you just turn your arm like this, you'll see middle finger, which indicates the direction in which the positive charge moves. The index finger, the magnetic field into board, and the force on the positive charge indicates that it will go to your left. Now, for the negative charge, again, which will move in opposite direction to the positive charge, force, field, current. The negative charge will move to the right by Fleming's left-hand rule. This is how we get these directions. A lot of information, very short time. I know, that's why you can always, rewind and look at it again. So, Fleming's left-hand rule is what gives us these directions. Now, that was for 3 marks. Just so you're aware, 1 mark would be for each direction or each emission. Now, they say in part 2 of A of this question, the magnetic field is replaced by an electric field as shown. Draw 3 rays to represent the path of each of the 3 emissions, again, alpha, beta, and gamma, as they pass through the electric field. So, the electric field is drawn on the diagram like this: positive, negative, and the emissions are here. So, as I said earlier, gamma is totally unaffected. Gamma, nothing happens to gamma. However, I included the charges here for a specific reason. If alpha is positive, alpha will be attracted to the negative portion of the electric field. And if beta is negative, beta will be attracted to the positive portion of the electric field, or to the positive side of the electric field. Effect of a magnetic field, effect of an electric field. In both cases, gamma is unaffected, and the magnetic field directions are opposite to the electric field directions. Beta goes to the right, in this case, in the magnetic field, and it goes to the left in the electric field. Alpha goes to the left in the magnetic, and to the right in the electric. Again, alpha positive, it will be attracted to the negative portion of the field. Beta negative, attracted to the positive portion. And this, students, has netted you 6 marks for this question so far. Well, I have to change my sheet of paper, and I have to continue with part B of the question, so don't go anywhere. Welcome back. We are now at part B of question 6, and it reads, an unstable isotope of lead, Pb210A2, undergoes exactly 2 sequential beta particle decays followed by an alpha particle decay. This is really a really lovely question. To become stable lead, 206A2Pb. With reference to the information in table 3, write the nuclear equations that will result in the formation of stable lead, 206A2Pb from 210A2Pb. Now, with reference to the information in table 3, and they politely ask you the first equation, the second, and then the alpha decay equation. So, what they've told us so far is that 210, A to 2. Pb is the symbol for lead. Goes through first beta decay. Then it goes through a second beta decay. And then it goes through an alpha decay to give you the end product of 206 A to 2 Pb. And what they asked in the question was the first equation, the second equation, and then the third equation. And in the table, what they gave you was bismuth, Bi, with an atomic number of 83. And I do believe it's polonium, an atomic number of 84. So, this is the information given in the table. And these are the steps taken to get there. This decays once, decays twice, decays a third time, and gives you this. How do we get there? Now, the first equation of decay would be from here. This is the first equation of decay. This. So, 210 E to 2 Pb basically decays to give you a beta particle plus something. Now, a beta particle is written as 0 minus 1. If you're wondering what these numbers represent, let me quickly explain. This is the mass of the atom, and this represents the number of protons in the atom. Mass, number of protons. Now, when balancing an equation of radioactive decay, you balance the top independently from the bottom. So 210 is on this side, and what we have over here is everything else. So 210 essentially is equal to 0 plus something. And surprisingly, that would actually be equal to, well, with reference to the table, write the equations that will result. I'm just reading the question again. With reference to the information in table 3, write the nuclear equations that will result in the formation of stable lead. Now, again, this will be 210 because you're balancing the top independently, and 210 is equal to 0 plus, well, 210. And A to 2 is equal to minus 1 plus something. Now, this is important, and it actually does trip a lot of students up. A to 2, I have to write it separately. A to 2 is equal to minus 1 plus some unknown. If we just carry this across the equal sign, it becomes A to 2 plus 1, which is equal to A to 3, is equal to the unknown. So this is A to 3. And I will just call this, for sake of argument, some J. So, 210 Pb breaks down by giving off a beta particle, one beta particle, to give us this. And then this now, in turn, breaks down via beta decay again to give us something else. So this here, breaks down via beta decay. Zero minus one again. and I will call this some K. And if we balance the tops, this is 210. If we balance the bottom, we get it to 4. So our first equation is here, 1. I'm sorry that this writing on a board thing, I'm good at it sometimes, but other times I literally just write all over the place. This is our first equation here. This is our second equation. The end product of our first equation is 21083, and I call it J. This 21083 that I named J breaks down via beta decay to give us 21084K. This is our second equation. And now I need to take something off the board, which is this, because I don't want to run into much difficulty. This now, this 21084K. Again, I'm naming it random things. This breaks down by alpha decay. Now an alpha particles are written as 4 to alpha. Beta particles are always written as 0 minus 1. That's how they're written. An alpha particle is a helium nucleus. It has 2 protons and 2 neutrons, hence 4, 2 plus 2, and the 2 again represents the number of protons. A beta particle, I nearly said beta decay, that would have been bad. A beta particle is a high-speed electron, and we represent an electron by indicating it is the absence of a proton, hence the minus 1. And that's how we represent these two. What we now do is assume that this that I named K breaks down via alpha decay to give us a new, or our final product. So 210 to 4 breaks down via alpha, which is written as 4,2. And to balance the equation, 210 minus 4 is 206, and a to 4 minus 2 is a to 2. And this is our final product. So, first equation, we lose one alpha particle, we end up with this. Second equation, we lose another alpha particle, we end up with that. And finally, why did I just say alpha? We lose a beta particle, we end up with this. We lose another beta particle, we end up with this. And we lose an alpha particle, and we end up with that. Beta decay, alpha decay. First beta, second beta, and one alpha. Beta, beta, alpha. And that is how we end up with our final product. I must admit, and I will say this, at times when you go in an exam, you will find that things look difficult, but if you just take it step by step and think it through, apply what you know. Beta decay means you lose one of these. Alpha decay means you lose one of these. You know these things. If you just apply these little principles, you're going to actually get where you're going. Now, forgive me for being terrible at chemistry. I am not going to say I know chemistry well. To me, I'm horrible at it. I just gave these two the names J and K because I don't know if you actually call them lead. I will be honest. I will admit that I do not know. However, the important thing about the question is that we start off here and we end up there. They said we start off with 210 to 2 lead and end up with 206 to 2 lead. We did that. So the steps are correct and right and proper. Everything was done as it should have been done. And that was worth 6 marks. 2 marks for this, 2 marks for this, and 2 marks for that. Now, The final part of the question part, he says, calculate the energy given off in a nuclear reaction if the change in mass is 0.3018 U. 0.3018 U. This is a teachable moment. Now, there are two types of, I'll talk while I'm cleaning the board. There are two types of nuclear reactions. There is fission and there is fusion. Now, fission is essentially the process, is the whole splitting of the atom, if you want to put it that way. Fission is when elements are, or one radioactive substance breaks down, and this reaction continues until all the matter involved is basically broken down. Fusion is a bit more difficult. I'm sure you've heard of the term cold fusion. Fusion occurs when you have several elements that are essentially combined, mixed, forced to change based on extreme conditions of pressure and temperature. The sun is a fusion reactor. I'm sure you understand the concept of extreme temperature when you think of the sun. And in each of these two nuclear reactions, both fission and fusion, mass is lost. Now you might be like, how is mass lost? Well, let me explain. So let's assume for any reaction, we have some material A and some material B. Then the reaction happens. And then we have some C and energy. Now, if we find the total mass before the reaction and the total mass after the reaction, we will realize that the total mass before is greater than the total mass after. This is what gives us the energy, because Albert Einstein gave us the equation E is equal to mc squared. Energy is equal to mass times the speed of light squared. That's essentially what he said. And this governs these reactions. The energy is produced when mass disintegrates. And the difference in mass is the amount of mass that has disintegrated. So, energy produced by a nuclear reaction is equal to the mass lost or disintegrated times the speed of light squared. This is how all nuclear reactions work, and this is how they generate energy. We have been told for our little equation that the mass lost is 0.3018 U. Now, you might be like, sir, why this thing is not in kg? When you're dealing with anything at this level, and by this level I mean anything on the atomic level, mass is not measured in kilograms. Mass is measured in atomic mass units, or AMUs. Now, 1 AMU is equal to, what did I put, 1.66 by 10 to the minus 27 kilograms. And the speed of light is rounded up to 3.0 by 10 to the 8 meters per second. So, we know mass, but in atomic mass units. And we have to convert this mass into kilograms. How do we do that? Nothing complicated, very simple. What we do is we just multiply 0.3018 times 1.66 by 10 to the minus 27 kilograms. Now, please note this is minus 27, not positive 27. That just goes to show you how small these atomic masses are. I mean, think about dividing something. Think about the grain of rice, and then think about breaking that grain of rice up into like 1 million parts. And you're probably still going to have more mass than this. You are going to have a lot more mass than that. So, time for us to do our calculations. This is where you need to have your calculators as well. I'm not the only one who needs to have a calculator. And I'm saying that because I left my calculator over there. 1 second. You might be like, sir, why did you do that? Well, you see, my calculator is on my phone. I'm a creature of the modern age, I guess. So, if you have your calculators out, you should have gotten the answer already. Let's see if I can get it myself. 0.3018 times 1.66. Minus 27. The answer I obtained was 5.00988 times 10 to the minus 28 kilograms. And this is the mass that was lost between before and after the reaction. This is the mass that gave us energy. This is that mass. Now what we have to do, or what we're expected to do, is substitute this mass along with this value into the equation. E is equal to m 5.00988 times 10 to the minus 27 multiplied by the value for speed of light. I'll write it back just so it doesn't look too far off. 3.0 times 10 to the 8 meters per second. But we have to square this. And I could tell you, hopefully, forgot my kilograms. Alright, this is going to be one large answer. I take that back about it being a large answer. I got 45.09 times 10 to the minus 12 joules. I hope you'd homework this. Now, just checking over my calculations again to make sure. 0.3018 times 1.66 times 10 to the minus 27. That is our mass times 3.0 by 10 to the 8 squared. Yeah, 45.09 by 10 to the minus 12 joules. That's a lot smaller than I thought it would be. But this is our answer nonetheless. The energy produced is 45.0 by 10 to the minus 12 joules. That calculation was worth how many marks? 3 marks, for a total of 15 marks for the question. So you have to convert mass, just recapping, you have to convert mass in atomic mass units to mass in kilograms. And then you have to substitute mass in kilograms and the value for the speed of light, which you will square into the equation. And then you multiply and you just get your answer. And that's it. This is the amount of energy produced in this nuclear reaction. I must admit that is a very small amount of energy, but that's neither here nor there. So we have worked question 6. I hope you learned something from it. I learned something from it. I learned that lead is 210 A22 Pb and also 206 A22 Pb. I learned that. I will definitely remember that. So again, do go over our calculations. Do try to replicate what we did. Use the formulae and use your knowledge as appropriate. And if you have questions or comments and you're looking at this on Facebook, feel free to ask questions in the comment section. And if not, get in contact with your physics teacher and you could ask them too. So the next question is question 5. Let me go switch my paper out, clean the board. I'll see you soon.